Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery.
Two solid rocket motors. That's a pretty rough ride, but you can feel the thrust tail off right before they separate. And you know, you get an indication PC less than 50, and then you know you're going to be there 2 minutes 5 seconds or so. They separate away. There's a huge flash in the front window, a big bang. You can hear the set motors push those away, and then it's just as smooth as can be on those main engines. They're phenomenal pieces of machinery.
The Space Shuttle main engines have been one of the brightest success stories of the Space Shuttle's 30-year career. Powered by a combination of fuel and oxygen, a single SSME, as the engines are called, produces about 500,000 pounds of thrust. Working with the 2 solid rocket boosters for the first 2 minutes of launch, 3 main engines push a shuttle up to Mach 25 and into orbit in 8.5 minutes.
We call the SSME an extreme machine, and it's extreme because on the inlets you got liquid oxygen and liquid hydrogen, and liquid hydrogen's minus 420 degrees Fahrenheit, so it's extremely cold propellant that we're putting through the turbo machinery, and then we're burning it in the main combustion chamber at 6,000 degrees Fahrenheit. So that's hot enough to melt iron.
It can do that without melting because the engine pumps the cryogenic hydrogen through a series of 1,040 tubes lining the nozzle. The supercold fuel keeps the flames from touching the sides of the nozzle. There also are a pair of turbopumps that move the propellants through the machinery and into the combustion chamber quickly. The turbopumps alone produce more power than a locomotive, even though they would fit on a desk. Providing that amount of power safely calls for extensive testing and inspections of each engine and their turbopumps. A main engine gets examined from the time the shuttle lands until liftoff. Highly trained technicians use long, flexible lenses called borescopes to look at each engine's insides for cracks and other defects.
A skilled technician engineer can perform a real good borescope inspection of bearings, seals, and actually the turbine blades, nozzle vanes, pump blades, and diffusers.
The engine's success did not come easy. Engineers began testing engine designs in 1975 at NASA's Stennis Space Center in Mississippi. Just getting the startup sequence right took months and months of complex work.
Well, of course, the first test of the Space Shuttle main engine on A1 test stand was like 20 milliseconds. I mean, it took a long time to develop the start sequence of the engine, and it was 20 milliseconds at the time, finally 40. They worked their way up to 1.5 seconds, which is a critical time period in the thrust buildup of the start sequence, and then it just went on from there, and it took a long time to actually finally get to main stage.
The shuttle's main engines made their first flight test on April 12, 1981, along with the rest of the Space Shuttle system. Although the engines had been fired on test stands, no crew flew with them until Commander John Young and pilot Bob Crippen rode them into orbit on STS-1.
And when that whole vehicle got together, we put the crew in and we counted down, and we saw engine ignition and all 3 engines come up. It was just an extremely rewarding experience to see that and see the SRBs fire and that whole orbiter take off and fly. It was hard to describe because of all of the activities that I know led up to that and all the people involved in it to see that as a successful mission, because we didn't have an opportunity to fly it unmanned before we flew it manned. So that's the first time this country really did an experiment with people on board, and it all worked.
Though the shuttle engines are smaller than the mammoth F1s that powered the Saturn V's first stage, they had to be far more efficient.
And then this was the first time we had to design an engine that would operate for 8.5 minutes. In the Apollo program, the first stage engines operate for about 200 seconds, and it basically gets you up to about 50,000 feet or higher through the heavy atmosphere, and then the first stage is spent and then the second stage takes over. In this case, the SSME was designed to start on the ground, have the ability to health check it before the solid rocket motors ignited, and then commit the launch, and then stay running all the way through orbital injection velocity, so that made it run for 8.5 minutes. So that was different than engines we had built previously.
Along with the brawn of hundreds of thousands of pounds of thrust, the engines carry very delicate brains that take constant measurements of the systems dozens of times every second.
This is the first engine we built that had an active onboard digital computer. And the computer has a program in it that runs through its full cycle in 20 milliseconds, so 50 times a second. It's out reading valve positions, sensor data, and we have algorithms in there that allow that engine to have what we'll call health monitoring. So we have active flight red lines that in the event that temperature should exceed the limit, that engine will automatically shut itself down to prevent a catastrophic failure.
No mission ever failed because of a Space Shuttle main engine, but a couple saw close calls during launch. In 1985, one of the engines on Space Shuttle Challenger picked up a problem.
So they actually shut that engine down at about 18,000 feet per second, let the other two engines run the vehicle until it reached the actual velocity required to make orbit. So it was a successful mission, and it just showed that the redundancy built into the engines really paid off.
The Space Shuttle's main engines also had a requirement no other engine faced before. They had to be reusable.
Reusability created issues with hardware embrittlement. It was hydrogen molecules embedding themselves in the material, causing embrittlement later on. So that created life cycle issues, and we were always talking about what's the remaining life in the hardware.
The SSMEs produce nothing but steam when they fire, another departure from previous rocket engines.
Oxygen, hydrogen, when it combines and creates water, it's very clean. A lot different from the Apollo days when you had liquid oxygen and kerosene. Well, this engine's extremely clean. And people are amazed when they look at the engines in the shop that have flown 10 times or more. They look brand new.
The shuttle main engines have proven to be extremely reliable machines with a record of reusability and success without parallel in rocketry.
But SSME is in a class all by itself. And of course, the reliability that we get out of the SSME is the reliability and the performance that allows the shuttle to fly.
As far as the extreme temperatures, the pressures they operate, the fact that they have been reusable and so reliable from STS-1 to STS-135, I still rate the main engines at the top.